Good morning. We are students from the Shatin College and our registration number is 51082. Today we are going to present our report, The Exploration on Odd Perfect Numbers. So what is an odd perfect number? Euclid first defines this concept in 300 BC. And a perfect number is equal to the sum of its proper positive divisors. For example, 6 is a perfect number because the sum of factors of 6, 1, 2, and 3 is equal to 6. So we define sigma n as the sum of all positive divisors of n. So a perfect number, omega, should satisfy sigma omega equal to 2 omega. In about 300 BC, Euclid first gave a method to construct even perfect numbers in this form. And Euler, in 18th century, proved that all even perfect numbers must be in this form. So are there any odd perfect numbers? It is still an open problem now. So we are going to investigate this problem by first finding the general form of the odd perfect number. First, we let the odd perfect number, omega, be the products of its prime factors. And the sum of factors of omega can be given by this form. As omega is as the sum of the factors of omega is a multiple of 2, but not a multiple of 4. So there are only one even factors in these products. And we let the first sum, this one, be even, and the others be odd. So alpha 1 is the only odd power, and the other alphas are even numbers. So alpha 1 is either in the form of 4 lambda plus 1 or 4 lambda plus 3. But if alpha 1 is equal to 4 lambda plus 3, then we can factorize the first sum into product of 2 even numbers. So it is a multiple of 4. And this contradicts with our assumption. So alpha 1 must be in the form of 4 lambda plus 1. And similarly, for P1, it can be either in the form of 4k plus 1 or 4k plus 3. But if P1 is equal to 4k plus 3, we can factorize the first sum into a multiple of 4. And it contradicts with our assumption too. So P1 must be in the form of 4k plus 1. And also, as other alphas are even, so the rest of the products is the rest of the products of the prime factors is a perfect square. So we can conclude that the odd perfect number can be reduced to this form: 4k plus 1 to the power 4 lambda plus 1 times m squared, and where 4k plus 1 and m are relatively prime. We thought that we discovered a great theory, but after that, we suddenly discovered that Euler discovered this form a long time ago. We were sad, but we were also glad because we have the same taste as Euler. But this form is very useful because we are going to investigate the property of the unit digit. The unit digit of P1 can be 1, 3, 5, 7, or 9. And the unit digit of m squared can be 1, 5, or 9. So in total, there are 15 combinations. And we will use the exhaustive method, trying to eliminate as many possibilities as possible. So we first consider this case when the unit digit of P1 and m squared are both 5. So P1 and m squared are the multiple of 5. So it contradicts with our assumption that they are relatively prime. So this case is eliminated. And also, if the unit digit of P1 is 9, then P1 congruence to negative 1 mod 10. So omega, the odd perfect number, is divisible by 5. This implies that m is a multiple of 5. So the unit digit of m must be 5, but not 1 or 9. And also, we pose some restrictions on other 4 cases. If the unit digit of P1 and m squared is in these 4 cases, we found that the unit digit of other pi's other than 1 must be 1 for some i's. So although we were hard trying to eliminate more cases, but it is rather hard for us. So we turned our attention to another approach, that is considering the multiples of the perfect number. Can we generate a larger perfect number from simply multiplication of a smaller perfect number? Are there any special properties of the multiples of an odd perfect number? So we first divide lemma 4. For any positive integers a and c is equal to a times b for some b greater than 2, then c and a satisfy this inequality. First, we let a be the products of its prime factors and b be the products of its prime factors too, and where k is the prime factors of b relative prime to a. Then, by the property of sigma function, we can break down sigma c over c into this form. And as this one is greater than 1, and this is greater than this one, we can conclude that sigma c over c is greater than sigma a over a. So we apply this inequality to perfect numbers. First, we let n be a perfect number, and m is equal to k times n for some natural number k greater than 2. So by the above inequality, we get sigma m over m greater than 2. So m must not be a perfect number. And after our submission of the report, we also discovered that the similar inequality can be applied to abundant number, that is sigma n greater than 2n, and the multiple of abundant number is left a perfect number 2. So now we discovered that the multiple of a perfect number is left a perfect number. But we believe that there are some special properties of the perfect numbers. Then we consider the k perfect number. A k perfect number satisfies this equation, sigma n over equal to kn. So if omega is an odd perfect number, then we discover that 2 times omega is a free perfect number because omega is odd, and then we can break down the sigma function in this way, and it is equal to 3 times 2 times omega, and so 2 omega is a free perfect number. And by that lemma, we can conclude that if the number of free perfect number is finite, then the number of odd perfect number is also finite too. And also, if there are n relatively prime odd numbers, and we multiply them together, and then we get a 2 to the power n perfect number. Let's consider the example. Let m be the products of these relatively prime odd perfect numbers, and omega m is equal sigma m, that is the sum of factors of m, is equal to this way, and that can be broken down into this form, and that is equal to 2 to the power n times m. So m is a 2 to the power n perfect number. So in conclusion, there are three results. First of all, we found the general form of an odd perfect number. Omega is equal to 4k plus 1 to the power of 4 lambda plus 1 times m squared. And we handled 7 cases of 15, and we eliminated 3 of them and posed restrictions on 4 of them. And the multiples of perfect numbers and abundant numbers are never perfect. This is useful in our future investigation because we can eliminate some numbers quickly. For example, is this number a perfect number? It is not a perfect number because it is a multiple of 945, which is an abundant number. And also, we found that 2 omega, that is 2 times a perfect number, is free perfect. So the number of free perfect number must be greater than the number of all perfect numbers. So in the future, we will concentrate our effort into the abundant numbers and free perfect numbers, and hope to get more results on the topic of the odd perfect numbers. So that's the end of our report. Thank you.